write down the formula that we just developed. So these are specifically for growth and decay situations, and these are specifically for simple increase and decrease with interest. So here's our formula. So an amount, a new amount, is based on a principal amount. That's what P stands for, an initial or principal amount, times 1 plus the rate, because you have your original amount with the interest added to it, and raised to the exponent of time, because you saw that that's how they combine over time as we start putting them together. This is only for things where interest is yearly, you're not putting in an extra money, you're not withdrawing extra money, and they don't do any compounding like we talked about before slightly. How I said my bank gives it to me monthly, that way I have a little more when they go do the next amount. So the first example is just kind of making sure that you know the formula and you know where things go. So it says you buy a savings bond. So a savings bond is like you buy it now for a certain amount and we guarantee that in this many years it goes up a certain percentage. And there's all kinds of accounts that banks have, CDs and stuff like that, that if you're willing to put a lump sum of money into an account for a certain amount of time, they'll guarantee a certain percentage investment, but you can't withdraw the money during that amount of time that it's supposed to sit in there. So you pay $25 and it has a yearly interest rate of 4.2%. What will it be worth in 15 years? So we're calculating a final amount given in a principal amount of $25. The yearly interest is 4.2%. Now, be really careful about this. Most interest rates are going to be given to you in a yearly interest rate. Even if they're compounded or something like that, they give you the yearly interest rate and then they would say, however, we compound it monthly or something like that. If they don't talk about compounding is when we would use this. If they say that they compound, we still have a yearly rate, but the number of times they do that calculation per year changes, and that's what we would look at. And then we know we want 15 years. So we have all the pieces for this formula, okay? You can write this a little bit simpler if you want, that this is a 1.042. Notice that this fits the mold of our exponential equations. This is an exponential equation with a base of 1.042. Is this growth or decay? Growth, because my base is more than 1, okay? So what's happening is my money is close to that asymptote, and then as I put more and more years, it's growing further and further away from it. So you guys would just put this into a calculator. I'm not really going to focus as much on the calculator work. If you struggle with the calculator, you can check along the way. You should get $46.34. That might not seem like a lot. You're like, I waited 15 years to get like $21.35 extra. But again, you did nothing, okay? And so it just grew at a certain rate, and then that's what you have. Okay, yes?
Does it matter like what time is?
It does. This is based on years with a yearly interest rate. If they gave you like a daily interest rate, you could use number of days as the time, because you know how we derived the formula over here was depending on that amount of time passing with that interest rate kind of matching up in those terms. Generally, interest rates are given in years, so our time is in years if we're dealing with an annual interest rate, okay? The way it might be different is like population growth, like bacteria. If you're studying something like that that grows very quickly, they would use like days or hours, but they would base their initial rate off of days or hours as well in order to plug in days or hours. Okay. All right. The second example says you open a savings account that pays this time 4.5% annual interest. Your initial investment is $300, no additional deposits or withdrawals, and you want to know how many years it's going to take for you to at least have $500, okay? So it fits the mold of our equation. It's talking about rates and times and amounts. So I know that I know that the interest rate is 4.5%. Sorry, let me write one step in here. So I know that in the parentheses, I'm going to have 1 plus 0.045. What is the initial amount that I'm starting with? 300. Do I know how many years I'm keeping that $300 in there? No. So I'm just going to make that T. Do I know the final amount that I want? $500. Now, this is going to mirror a lot what we did yesterday to find intercepts.
Wouldn't it be like 500 is less than or equal to?
Yeah, so what I'm basing it on by using equal to is that we want to make at least 500. So it would actually say 500 is greater than or equal to this amount. So I'm finding the break-even point. Like, tell me exactly when it will equal 500. I know that after that many years, I hit 500, and after that, it would just be more. So even though they're saying at least, I'm going to find that minimum point and say then at least this many years. Is that okay? All right. So this is going to look a lot like our intercepts from yesterday if you were looking for an x-intercept. But yesterday, we had really nice numbers. And here is an example of real life. Real life numbers are never as nice as the numbers we give you in math class, okay? So yesterday we had things like 2 to this power equals 4. What power does it have to be? Well, it has to be 2, and it all worked out really nice and simple like that. Now, if we were to get the exponential part alone right here, because we're trying to solve for t, so we're going to try and get the power alone. The first thing we'd want to do is divide by the 300, so I'm going to go ahead and do that. And then I would have this equation that says 5 over 3 equals 1.045 to the power of t. So yesterday, this was a 2, and this was a 4, and this was a 2, and this was a 1. So we could figure it out with our number sense and our exponent rules. I have no clue what power you put on 1.045 to make 5 over 3. So you have kind of two options here. Okay, option 1 is guess and check, enjoy, okay, whatever. There's actually 3. Third option is algebraically, but you have to learn a whole new function. We are going to do that in this unit, so that's why you're seeing this kind of stuff. Option 2, what you can do right now, okay, is you basically want to figure out when this exponential function reaches this value, okay? So what we could do is we could actually solve it graphically if we used our calculator. I'm just going to make a note about how to do that because you guys should already know how to do this. And my goal right now is not teaching calculator, but teaching exponential functions. So what you would want to do on your calculator is you would want to go to the graph, and like in Y1, you'd want to type in your exponential function, okay? And you want to know when it reaches 5/3. Now, you can use a lot of tools on the calculator, like the table and stuff like that, and see when it gets close to 5/3. But the best way to get an exact answer is then to graph as a separate function 5/3. What is 5/3 going to look like on the graph? Y equals 5/3. A horizontal line. So all it's doing is setting a boundary for me, like, hey, you have your exponential curve. Here's the amount you're looking for it to equal. So what am I looking for when I'm looking for the solution? Garen? Yeah, when they cross each other. And then remember on our calculator that has all those things we can calculate, like maximums and minimums, and it also had something called intersection. So you're going to find the intersection point, and I'm going to tell you guys what it is in this case. In this case, if you did all of it correctly, you would get an intersection point of 11.6, 1.67. Now, one of these numbers should not surprise you, this y value. 1.67 is 5/3 because that is a constant function. Its y values can only be 5/3. So that is not surprising. Then you have to interpret from this. So this is going to give you the answer. But what part of this is the answer? What were you looking for? Okay, you were looking for the number of years. The number of years for us is t. Was that t an x or a y in our equation where we used it? It's an x. So really, x is telling us the number of years in this situation in our solution. And so we would focus on this number here, and that would tell us that it takes a little over 11.5 years. Okay, maybe if we only get our interest at the end of the year, we'd have to keep our money in there for 12 years, depends on the situation, for us to get $500 from our $300. Okay, is this all right with everybody? okay? There will be an algebraic way, but we have to learn a whole new function and understand it in order to do that, and that's going to take us a little while. So right now, technology and all of our application problems, clearly I would not expect you to calculate this by hand from there, okay? We're not going to by hand calculate 1.042 to the 15th power, okay? Something like that. All right, last problem that we're going to look at tells us the initial value of a car is $30,000. After 1 year, the value of the car is $20,000. Estimate the value of the car after 5 years. So it's an estimate because we can't totally control the economy and like appreciation and depreciation. Now, the words I just said, appreciation means things are going up in value. That's to appreciate in value, not like I appreciate you, but like it's appreciating, okay? So when I use the word depreciate, that describes this situation because what's happening with the value of the car? It's going down, okay? All right, so when I look at the problem I'm supposed to solve, I'm supposed to find the value of the car after 5 years. So I know I started with $30,000. I'm looking for the value of the car after 5 years, okay? What they didn't mention at all is any rate. So I come across a bummer as I try to just like jump in and solve the scenario, right? The fact that I don't know the rate at which it's going down in value, and without that, I can't really determine an estimate for its value. But they did give me some other information in this problem that doesn't actually answer their question. What's the other information that they gave me? Sammy? Okay, yeah, so he sees that 20,000 that you guys see after the first year. It went down by 10 grand that year. Okay, so there's a way just by looking at that to know the rate of depreciation. If you were being very algebraic about it, what that 20,000 is really telling you, separate from that one, because this is not about 5 years, this is a separate scenario, and I'm hoping it gives me some insight, that I know that it ended up being 20,000 when it started as 30,000. Still no mention of the interest rate, but that was after 1 year, okay? This equation that I want to solve is currently not solvable, but the second equation I wrote is solvable, and specifically, what does it tell me? What am I going to get when I solve this second equation that I wrote? The rate. I'm going to be able to solve for R, which is the rate, which is the one thing I'm missing in my first scenario to be able to answer their question. So this is actually going to work out well. I'm going to divide both sides by 30,000. And I'm going to get that 1 plus R, and I'm going to be super thankful they gave me a 1 year piece of data instead of like a 5 year piece of data, so I don't have to deal with any radicals or anything. Okay, so 2/3 is equal to 1 plus R, and if I subtract 1, then I get that my rate is equal to negative 1/3. Now, does it make sense in this scenario that the rate came with a negative? Yes, because this isn't appreciating, it is depreciating. What that means when I go to finish solving this amount over here is that I'm actually not going to have 1 plus the rate. I'm actually going to have 1 minus the rate, which should make sense with what we talked about yesterday, because that makes our rate 2/3, which is smaller than 1, and makes this an exponential decay scenario rather than a growth scenario. Should this be a decay scenario? It should. My car started as 30. You know that old, they say the saying, like, once you drive a car off the lot, it's lost of its value, whatever, right? So like cars classically are something that depreciates in value. This should be something with a rate that is showing decay rather than growth. And then I would go ahead and put into my calculator that or this version if you wanted in order to find the amount that the car would be worth. And sadly, you should get something like this. Yeah. Want. $3,950.62. Now you might think that's extreme, but number one, if you are headed towards car shopping, you will see the extreme price difference on some vehicles. It really does depend on the economy and the type of vehicle, but on some vehicles between buying it new and buying it used, especially if it has certain miles or certain years that have passed on it. Secondly, look at what the depreciation rate was in this case. It didn't go down like 5% of its value each year. It went down 33% of its value every year. That's a lot. Okay, so I'm okay with the drastic difference because if every year it's losing a third of its value, okay, it is decreasing pretty quickly. And for those of you out there being like, if it lost a third of its value every year, there's none left after any years, remember, it's using a third of its current value, okay? So if I start at 100 and I lose a third of my value, I'm at about 66. The next time I take away a third of the value, I'm not jumping all the way down to 33 because I'm not losing a third of my original value. I'm losing a third of my new value. Okay, and that's why it gets really close to the asymptote but never crosses it, because you're getting infinitely smaller, but you're never reaching zero because you're not subtracting things. You're taking a percentage of them. And because you started with something, a percentage of something will always be something. It won't be zero. And that's why you're getting closer and closer to that asymptote without crossing. Okay? Is this okay with everybody for what's happening here? All right, so